Now we are going to study the hybridization of methane using group theory. Okay, the central atom of any molecules with more than two atoms can undergo hybridization. So this concept is invoked to explain the strong nature of bonds and their directional nature. So in such molecule, the hybrid orbitals are used as the basis for the representation to determine the symmetry of hybrid orbitals. So let me consider that the methane has four hybrid orbitals. They are represented by pi 1, pi 2, pi 3, pi 4. Pi 1, pi 2, pi 3, pi 4. It has the point group of tetrahedral. Okay, it has the symmetry element of E, C3, C2, S4 and sigma D. So, this character representation of such hybrid orbital is obtained by performing the symmetry operation on hybrid orbital and deriving their respective transformation matrix or by using simple methods like this. That is the character of that particular symmetry operation. It is the character. This is the operation performed by using the symmetry elements in the point group tetrahedral. So the character of that particular operation is equal to the number of orbitals which does not change the position and direction minus the number of orbitals which does not change the position but simply reverse in directions when symmetry operation is performed. So in this way we have to find out the character of that particular symmetry operation in tetrahedral point group. Next, the character of that operation of E. Okay, the character of E has 4 minus 0 is equal to 4 and the character of C3 has 1 minus 0 equal to 1. Okay, the number of unshifted direction is equal to 1 and C2 character will be 0. Both are the changed. And the character of S4 lead to also 0 and direct character of sigma D has the value of 2. So the reducible representation for that above symmetry operation is the E has the value of 4 and C3 has 1. In tetrahedral geometry, we have 8 C3 axis. Okay, and we have the 3 C2 axis. It has the character value of 0 and 6 X4 axis. It has the value of 0 and 6 sigma D symmetry operation and it should have the value of 2. Next, this is the complete character table of that tetrahedral. Okay, by using the orthogonality theorem and the character table will be reduced into particular irreducible representations. We are very well known the 4 rules of that character. That is, the number of irreducible representation is equal to number of classes and the sum of square of dimension is equal to order. The next, the sum of square of character of all irreducible representation is equal to order. And all the irreducible representation are orthogonal each other. Based on these 4 rules, we have to find out the character value for tetrahedral. So now we are already find out the reducible representation for the tetrahedral point group, that is E has 4 and C3 has 1 and C2 has 0 and S4 has 0 and sigma D has the value 2. This is the character value for that particular symmetry operation A1, A2, E, T1, T2. It has one dimensional symmetry and triply degenerate, okay, triply degenerate and doubly degenerate symmetry element. So already told you know that is 1 and 2 subscript will be designated to mention the symmetric and antisymmetric nature with respect to the principal axis. Okay, the next we have to how to find out that reducible, that is hybrid orbital involved in the irreducible representation. First, we have to find out the number of A1 present in tetrahedral point group. So the total number of, okay, the total class of the symmetry element of the tetrahedral group is 24. So we have to add 1 by 24 into 1 into 4 into 1. 1 is the character value of A1 and 4 is the reducible representation for the identity element E and 1 is the coefficient terms of value E. Okay, the next we are adding 8. Okay, 8 because 8 is the 8 C3 axis and the reducible representation value will be 1 and the character value will also 1. Similarly, we have to put by using the character table value. Finally, we got the value of 1. That is the tetrahedral having the 1 number of A1. Okay, the next, how to find out the A2? By 1 by 24, 1 is the coefficient of that is character value for identity element. 4 is the reducible representation of the identity element E and 1 is the coefficient terms of the identity element E. And second one is 8 is the coefficient term of C3 and 1 is the reducible representation and 1 is the character value of that is C3. Next 3 is the coefficient term of C2 and 0 is the reducible representation and 1 is the character value for the C2 operation. The next one is 6 is the coefficient term of S and 0 for the reducible representation and 1 is the character table value for the A2. So finally we got the value of 0. Similarly, we have to put the value of the corresponding coefficient or reducible representation value and character value by using the character table. Finally, we got the number of A1, A2, E, T1, T2 is present in the tetrahedral point group. Finally, we got that is 1 A1 molecule is present and 1 T2 is present. T2 means it is a triply degenerate. This is one-dimensional symmetry element. So finally, we have got the reducible representation of hybrid orbital A1 plus T2. A1 is the most symmetric representation, so it must be correspond to the highly symmetric s orbital. So this is the complete character table. Okay, we are very well know. So by using this character table, we have to find out the hybrid orbital of that methane molecules. So from the character table of area, that is by using this area and this area, we have to find out the number of hybrid orbitals present in methane molecules. By using the character table of area, that is 3, the x, y, z vector corresponding to the T2 symmetry, that is triply degenerate symmetry, which represents the px, py, pz orbital. So the hybrid orbitals are formed by mixing. We are already know it has the symmetric s orbital. So we have one symmetric s orbital and 3 p orbital, that is px, py, pz. So finally, based on the area 3, we have find out that this methane has sp3 hybridized solutions. So from the character table of area 4, the area 4 indicate that xy, yz and xz for T2 symmetry. It represents the orbitals are projected along xy, yz and xz plane. The corresponding orbitals are dxy, dyz and dxz. So finally we got based on the area 3, the hybridization of methane is sd3. From area 3 and 4, we have got two different hybridization. From area 3, we got sp3 hybridization. From area 4, we got sb3 hybridization. Which one is correct? By comparing the area 3 and 4 in character table, we conclude that in the carbon atom, the excitation of electron from the 2p level to 3d level involves higher energy. Okay. In the carbon atom, the excitation of electrons from 2p level to the 3d levels involves higher energy. So the sd3 hybridization is not a favorable one. So even though it is symmetrically allowed. So finally, we have concluded that the methane has sp3 hybridization. So this hybridization will make symmetrically and energetically allowed one. So finally, we have got the methane has sp3 hybridization. Thank you.